Your time now.
All right. Thank you, Stefano, for the opportunity to speak to your group and those other people around the world to join this seminar. As Stefano mentioned that, and he and I, we collaborated back many years ago. We had one paper on the light stability of elements. That's the foundation of carbon modeling, which now I've been working on for many years. And this is my second time to give a talk which is titled Entropy. It's one word only. And as Stefano mentioned that I received the ASM Gibbs Award, that was 2014. I give the talk, was Entropy. The title was Entropy. That's the first time I give a talk with only one word. And now the second time. So see, I hope in case you have heard my talk in 2014, 7 years later, you will see that we learned a lot more about entropy, even though entropy is a very, well, I would say old or very traditional concept, but there's still a lot of new things to be learned on entropy. Okay, as Stefano mentioned, my name is Zi-Kui. I'm from the Pennsylvania State University, and the website here is our group website. And of course, the work Stefano mentioned, we have over 500 publications, actually close to 600 now. Of course, I have to have a lot of collaborations. I have a huge number of collaborators. But for today's talk about entropy, I do want to emphasize one person, one collaborator I had, which is instrumental to get this entropy working down in the last 20 years. That's Dr. Yuan, actually Professor Yuan. He's a research professor at Penn State. We have been working together since 2003. And the paper is here. Look at Stefano's paper. Okay, that's paper is Stefano. And back in 2004, Yuan was first author. I get our work done. So this is very, very important work. And we constantly go back to that data to understand more what's going on. I want to thank Yuan for working together for the last close to 20 years now. We're still working together, so that's great. A lot of new work we're doing. All right, so I want to first emphasize that entropy is mod scale. The background here, of course, is not what I created. It's from the Microsoft PowerPoint. I thought this diagram looks very nice. As you can see that you have very small scale and a larger scale and across multiple scales. That's what entropy is about. Okay, I also wanted to emphasize entropy is multi-scale into two books, which I guess many of you have read already. One is a book by Stephen Hawking, talk about the brief answers to the big questions. Okay, in that book, or in a number of his publications, he talked about entropy and information of a black hole. That's a pretty big scale, right? It's a huge scale. Okay. And there are many books about entropy. But recently I read another book, I listened to another book called The Order of Time. Okay. This is a recent book. I like the quote here. The physics has found its pole. Oh, that's pretty interesting, right? And in this book, the author talked about entropy. I quoted two statements from the book. One, entropy drives the world. The world could be small or big, right? But it's all driven by entropy. Another very interesting statement in this book, I'm sure in many other books too, the time slows down when you move faster. Okay? So that's also a very interesting statement. And it seems that it means that if you do things faster, you actually have more time. That's also a very profound statement. Okay, so now go back to what we call entropy. Entropy is a part of thermodynamics, right? And we all learn thermodynamics. But I do want to quote one statement by Einstein. It says the law of thermodynamics is the only physical theory of universal content. which he was convinced that within the framework of applicability of his basic concepts will never be overthrown. So that means universe divided forever. And it was when I teach my thermodynamics, I was using keys as example and to say how entropy works. So my students all know that story. And yesterday I got an email and talk about entropy of thermodynamics. It says, baby loves the thermodynamics. And why they do that? Because they produce entropy all the time. They make a mess at home, and what do they do, right? So they're following thermodynamics, produce entropy. I thought that's a very good book. I haven't read it yet because I just saw it yesterday, but I found the abstract, you can see that. So this is a very important lesson to young people here. Some of you married, some of you not married, some of you have kids. So your kids make a mess out of your homes and or destroy things. That's what they're designed to do because they produce entropy. All right, so what do we learn about S, the entropy in our work, in our study? So we learn this one. This is the first time we probably saw it or see it. And the ds equals delta Q divided by T. Okay, that's the first time probably, you start with first law, then you get this introduced. And then when you become a little bit more into thermodynamics, you learn this one. Oh, you said G, based on Boltzmann distribution, you said S equals KB log omega. All right. But there's two main things we learn in terms of thermodynamics. However, if you look at the two equations, you see that there's not much scale here. And this is not explicit. Okay? So that means it's hidden somewhere, right? It's hidden somewhere inside these kind of equations. So I hope today's seminar I'm going to give will kind of, make us understand a bit more on this kind of large scale feature of entropy and how we can predict it. So in terms of that concept, so we wrote many papers on this topic, but the latest one we had is 2019, and it's called large scale entropy and its implications to critical phenomena, emerging behaviors, and information. That was a paper written for John Morrow, and unfortunately he passed away recently for his Gibbs Award Symposium. As you can see, that I have three authors in this book, in this article, me and Bingley is a professor from statistics. And Henry Lin is a professor from Department of Ecosystem. He works on forests. Right? Unfortunately, Henry Lin also passed away, I think it was last year or year before last year. So we wrote this book. So what is the idea in that paper? This paper, sorry. And it's written about this one. When we talk about entropy, we talk about a scale, at a certain scale. We talk about a K scale, for example, here. We have a lot of configurations, okay? And then for this configuration, we say, okay, now we have entropy. So what is the entropy of this scale? First, each configuration has its own entropy, right? Has its own probability. And then they configure each other together. So the entropy of this whole system is basically the entropy of individual configurations, and they are configurations together. Right? So two configurations kind of thing together. Of course, now for each configuration here, they have sub-configurations, right? So they have 1 to n configurations inside that configuration. Okay. So now that is for each SK, there's entropy in that scale. Okay. So then we can do same decomposition, right? There will be again this configuration has a sub-configuration, so we got SL with their probability, and with their configuration, which is KB log the probability of L. So you can see you can divide all the way down. Okay, of course, now when we talk about the materials science or combination physics, we go to atomic electronic scale. That we got density function theory or Schrodinger equation. But you think about that, if you go to the black hole, what? That means you have some upscale there, right? Large scales here. So that large scale will also affect our scales we have here. So it's like an interaction there. interaction. Sometimes, of course, you define your system here, then that part will be your surroundings, right? But you can change your system, so you can include that surrounding into your system. So it depends on what you want to investigate. You can really, see which part is surrounding, which part is your system. So this is what I think of multi-scale. Now the question is, how do we calculate all of them? Can we predict all of them and then connect with what we observe? Okay, so let's get the first term here. The ds equals delta Q divided by T. So what this equation really means is that it's entropy change due to the heat. For example, we got a heat from sun to earth, right, every day. So the entropy for that heat in the sun is smaller because heat is higher. So when that heat comes to earth, temperature decreases, entropy increases. Okay, so that's actually a perfect example of how the nature works. And however, if there will be also change of mass between the system and the surrounding, then we'll have to add this component, which gives the entropy of a component and times the change of that one. It's very interesting. The change could be either you lose the mass or you get the mass, right? So that means have different value. So SI would be with the partial entropy, could be either partial entropy of the system or partial entropy of the surrounding. They may not be the same unless they're in equilibrium. And then in this case, we define chemical potential is mu I equal to UI. UI is the partial internal energy of that component. Again, it could be the system or the surrounding, depends on whether you add a mass or you remove the mass. Okay, so now is that we haven't talked about system's equilibrium now, right? Now, if it's not equilibrium, you don't have to add another component of the entropy. It's called entropy production. Because if the system is changing inside, you have some internal processes which are irreversible, they can produce entropy. So you now see that the entropy of a system has three components. Entropy, right? You have the heat change, you have the mass change, you have the entropy production. Okay. So if we put all three together, then we'll have a complete picture of the entropy of the system. All right, so this is basically the extension of the simple equation we learned from the first few lectures of thermodynamics. Now you see, we start from the simple one and ends up with this very complex one. Okay, it's pretty very complex as a system, particularly this one, the internal entropy production. Okay, let's look at the second one. S equal to KB log omega, right? That's also an equation we learned at the early days when we start. And then it has to be very clear. This is at a specific scale we're talking about. That's omega is a configuration at that scale. It's a statistically equivalent configurations. That means that all the configurations have the same probability to exist. Okay. For example, again, this is our typical thermodynamic lecture. We talk about the ideal mixing in a multi-component system. So then S equal to minus KB, Boltzmann constant, a summation of XI log XI. That's XI is the mole fraction. However, if the configuration is not equivalent, then we don't use omega anymore. We use probability. Okay, so basically the entropy at that scale is the minus KB, the summation of the Pj log Pj. That's the probability of each configuration. Of course, if all the probability are the same, then it goes back to this equation. So see, now this equation has two very important characteristics. First, it's at a specific scale. Second is for statistically equivalent configurations. Now we know that nature is not going to be like that, right? Nature is going to have different different scales, as I mentioned. Then it has different configuration probability. So put them together makes nature very interesting and complex. Now, to scale, it's really have to actually two scale. It's space and time. Okay. Of course, if you go to relativity theory, space and time are together, talk about the gravitational forces. So that means our measurement is very important for us to understand our measurements. Our measurements are average over space and time. So all the measurements we do are over average, over certain space, certain time. So then let's talk about spatial resolution. We can naked eye, we can see, we can optical, SEM, and TM. Okay, so we can see a angstrom level today. Or we can do electron level to infer, not directly, but indirectly we can do that too. And then for time resolution, something very, very important. Okay, so X-ray crystallography, we have a time resolution, spatial resolution, synchrotron, we have another one. Okay, but I do want to mention a very important technique called X-ray absorption spectroscopy. That one measures local geometric. Okay, that's a sub-angstrom level measurements. And another the subset of this one is X-ray absorption fine structure, XAF. XAF, that's a very important tool too. Okay, to illustrate that example, I want to give one material. It's the titanate. It's very electric material. We know that at a low temperature, lead titanium is very electric. What it means is that you have lead, titanium, oxygen, get a kind of a cubic structure at high temperature. But at low temperature, the titanium atom moves away from the central point. Okay, so it distorts the lattice into tetragonal, and also displace one, get a ferroelectricity, polarization. So two things, you distort the structure, and it also displace the atom. Okay, so it's a tetragonal with polarization. Okay, then at high temperature, we say, oh, now it becomes cubic. Okay, so this cubic, this is tetragonal. All right, so let's look at the experiment. So the measurement was done in 1950s. You see that if you make the titanate, if you increase temperature, you have CA ratio. This is C, this is A, it's tetragonal. If you do the volume, this is A squared C, which is 1/3. You see that it's tetragonal, but CA ratio becomes smaller and smaller, and then you become cubic. Now you see the volume will decrease, as you hear, the volume decreases, and then start to increase. So this, of course, done by X-ray, 1950s. And you can also study the heat capacity. You see a second order transition, and you see you get a spike of the heat capacity. So that's well understood. We have when you become cubic, you lose the ferroelectricity, electrical property, so it becomes the titanium move to central position. So that's we understand how the ferroelectric transition. However, if you do the XAF measurements, you look at the titanium edge. What do you see? You see that again. This is CA again. These lines are from the X-ray I just showed. Now look at the C ratio. C ratio basically C axis basically means the C axis locally. You see that it almost does not change. And way above the ferroelectric transition temperature. For A parameter, last parameter, same thing, it stays there, right? And look at the average of CA, well, the volume decreases a little bit here, and then starts to go up here, and it continues to go up. So now you see you got two different measurements of the same material. One is X-ray, and that is XAF. So what do you think, right? We always believe experiments are all correct. So both are correct. So the differences now is the resolutions we have. The spatial resolution and the time resolution. Okay, now you look at the polarization. Again, we said the conventional view is that above the ferroelectric transition, you have no polarization anymore. That's right, because overall you don't have any more. So that's the X-ray measurements. That's the neutral measurements. You see that it goes to zero. That's right. That means look at the whole picture of the titanium is zero. However, if you look at individual titanium atoms, what do you see? It's go here. So titanium is still dislocated or displaced. It's not at a center position most of the time. That's because the XAF measurements get much higher time resolutions and spatial resolutions than the X-ray. Of course, now we can do ab initio simulations. We take an AMD simulation. We fix the overall shape from the X-ray data. That means the the whole system is constrained by the X-ray data. Okay, but we let the atom, move. You say initial molecular dynamics. That means you do not fit the atomic force. You take the quantum mechanics, DFT, calculate the force. Now, of course, now you can move. You can follow the titanium atoms, right? You can follow it. You can follow the distance between titanium and the oxygen. Atoms, movement by movement. So the result is, this is at 623. It's just slightly below the transition temperature. What do you see? We have three colors here. Basically three atoms, titanium. You see the green one, so it's C, but it then jumps. You see it jumps there, right? It jumps. So C, and also the red one, but the blue one jumps less, right? It jumps sometimes, but not very often. So what it means is, but this one jumps off here too, right? Now suddenly, the titanium was kind of vibrate and start CG. It's going to change. You can change that position now, so it becomes tetragonal at the time. And for some time, then here again, right? Now, if you move closer to the transition temperature, almost, I think it's about probably 1-2 degrees above it. What do you see? You see that the jump is much more frequent. Okay, so now if you do X-ray analysis, it's probably just average out, right? Because the X-ray resolution is not that high enough, you can really capture those atoms, the jump. Okay, so what it means is that if you do the stat analysis, you find that, because remember that we take the X-ray CA ratio for the overall supercells, and then what do you find? If you do the analysis, you find that C is always have a polarization. CA is tetragonal. So it's tetragonal and way above the transition temperature. It just flips more frequently. So X-ray cannot detect this flipping. I think it's always a C position. Because flipping has to go this way and the other way, right? So you have to go through that cubic structure position. The reason is because X-stuff can look at very high time resolution, very high spatial resolution compared to X-ray. So look at the polarization, the same thing. You see X-ray polarization, neutron polarization, and the X-sub polarization, and the MD simulation polarization. Okay, now it gives us very, very interesting understanding that what we see is always average of the time and the space resolutions of that technique. So that's of course we know that already, right? But it's just the very important experiment data and computational data to show that that's the case. Now, so let's talk about multi-state configurations then. Okay, so now when we do DFT calculations, we do the thermoelectronic contribution. Okay, we can do integration of the electron density of states. We can calculate the entropy contribution from thermoelectronic contributions. And then we do photon contribution with the atomic vibrations. Okay, again, it's still the same probability. Okay, it's same probability formula. The pi log pi. For both equation is identical equation formula-wise, but just given the quantities you have there. Now, that's what we do with the quasi-harmonic, right? For this kind of, but now we have to go one step above now, right? For example, when we talk about that time day, these two are not enough. We have to think about how do we consider this change of titanium in this direction, go to that direction. Now, for one direction, we can go to we have 6 directions, right? C plus C plus A plus minus A plus minus B. So I have 6 directions to go. So that increases our configuration. Okay, so that configuration cannot be captured by the quasi-harmonic. Okay. And of course, we do class expansion. We're going to class variation that gives us pairs, triplets, and tetrahedral. Okay, again, that's still limited, right? Because look at the supercell we have. We need so many titanium atoms to see the collective behavior. So that's what our approach. We use a partition function approach, and larger than above. Okay, and with spin configurations. So that's really the major approach we have talked about. So we call it multi-scale entropy approach. And we try to figure out a name for this one, even though we have been working on this one for many, many years. We are thinking maybe we should call it a Zentropy approach, multi-scale entropy approach. We will see how that name is accepted by people. As you see here, we started working on this one in 2008. It's first paper by Professor Yi Wang. And we're still publishing papers in that topic. So it's still evolving, including the name. Okay, so it's based on the partition function in terms of free energy. And if you look at the literature, most of the partition function approach is based on the energy, not the free energy. Okay? We found that it's necessary to use free energy to do the partition function. What does it mean is that we know this already, right? We know this already. Partition function equals to free energy of system divided by KBT exponential. And then we talk about Zi-Kui, that's the partition function of individual configuration. And most of the time, people use only energy here. But we found that we actually have to use the free energy to make the prediction closely in agreement with the experiment. And also, we think it makes sense to have free energy instead of energy. Now, of course, you can just flip aside, you get free energy of the system, which is KB log, KBT log Z. And then, now it's very important here that the free energy of the system is the free energy of the different configurations with probability, and time is a new term. The term, of course, has been there implicit in many calculations, but when you take it out, it becomes very important. So it's the probability of the different configurations we have here. Okay. So that one plays huge important role, as we will show in our work. So this we call it, but this is the configurational entropy, right? The term is I showed in the previous. So the configure. Let's go back to the equation I showed earlier, multi-scale. So that's how we derived it. We derived the entropy of the system is equal to the entropy of the individual configurations, weighted average with the probability of each configuration, and plus a configuration due to these configurations. Okay. So we call it an entropy approach. This one. Okay, so we did a few examples. Phase one. So one, we take a relatively simple case, cerium. Well, actually, cerium is not very simple, but it's relatively simple because it's pure element, right? But it does have some challenges. So one name is F electrons. It has F electrons. So we have to use the U parameter. But I'm thinking maybe we can remove the U parameter now as we understand more. But anyway, we use the U parameter. And there's magnetic transition. Magnetic transition we know is very hard to predict. And then even more difficult, it has a critical point. Okay. And then if we extrapolate this two-phase equilibrium all the way to 0 Kelvin, you get a transition between these two states, which is non-magnetic to ferromagnetic at 0 Kelvin at the negative pressure. That's actually very interesting. This is one of the elements, or the only element in the periodic table, which is non-magnetic at 0 Kelvin, becomes magnetic at high temperature. That's a very unique element. Very unique element. All right. So now you see we have two states, right? Two configurations. We have a ferromagnetic configuration. We have a non-magnetic configuration. So again, we can take our approach, right? We take the free energy equal to 3 components, 0 Kelvin energy, and with vibrational, with so many electronic contribution. Put them together, we calculate the photon. It's not bad. It's pretty good. So this is the experiments, and the red one is magnetic, and the blue one is non-magnetic. The measurements is at the magnetic room temperature. It's pretty good fitting. So entropy looks very nice. Looks very nice. And again, this is from the paper 2008, and Dr. Wang was the first author of this paper. And however, if we take this approach, we calculate two structures, right? We take the non-magnetic, paramagnetic, and magnetic, put them together. We got not too bad. We got a good phase equilibrium here. Remember this FCC, both FCC is a miscibility gap. But these two never come together to get the miscibility gap, get the critical point. Critical point is around here. It never goes there. Because it's always parallel, because it's always first order transition. So I have to be able to make it into the second order transition, right? That's what the critical point is about. Of course, now we look at the literature. Dr. You want to look at the literature and say, okay, how do we handle magnetic property? Well, we know that. Look at the literature, people do magnetic like this, right? Oh, first of all, do negative pressure at 0 Kelvin. If you do the two EV curve, okay, so the dotted one is without a 0-point energy. The solid one is with a 0-point energy. You do the common tangent, you get -0.87 gigapascal. It's very nice. They agree with that extrapolation very, very well. So that's actually how we get the U parameter. And we use U parameter for that to get that extrapolation correct. And now for the magnetic, we say, okay, look at the literature, how people do that. You take the additional magnetic term contribution, which is KBT log 1 plus the spin moment with the orbital angular moment minus the spin moment. That's people use in the literature. So we add this term into our magnetic energy, into the ferromagnetic system, the configuration. Okay. Then we take our mixing, right? Take our mixing. Okay. Now you see that if you do different temperatures, 0 Kelvin, 100 Kelvin, and so forth, you see this sign shadow is this entropy contribution between two configurations only, with non-magnetic, non-magnetic, ferromagnetic with this contribution. So this is what is this term? This is actually about the magnetic disorder. This is entropy. This is magnetic disorder entropy in the ferromagnetic state. Now you see that because of these two combined together, and this portion becomes bigger and bigger. So if you know only two configurations without this entropy, you have this cross point, right? It'll be always first order, never be second order. You get a common tangent. However, because of this entropy term and the energy, since the energy is lowered, you get a critical point. Critical point is 476 Kelvin with 2.22 gigapascal. Actually, yeah, so it's pretty good. The experimental value is about 2 gigapascal. Okay, temperature is also very close too. So we are pretty happy on that. However, we're still not happy. So that means this is the mean field theory, right? This is not the quantum mechanics. Well, it's not from first principles. Okay, so not first principles. We're thinking what it can do. Oh, but I wish more published. Actually, the proper prediction was beautiful, right? The emissivity gap, critical point, and the critical point is divergency. You see divergency, the V to P derivative is infinite. Okay, and all the experimental data were very nicely predicted. Okay, so it's completely predicted with that mean field approximation we had for the magnetic spin change. Okay, so now look at this term again, right? So this is really about the mean field magnetic spin flipping. It's talk about the spin configurations. Now we talk about a non-magnetic, we talk about a ferromagnetic, but we know that when the non-magnetic and the ferromagnetic come together, you could form antiferromagnetic, right? Okay. You could have ferromagnetic or paramagnetic. So that means there are a lot of more spin configurations. Take the three groups: non-magnetic, ferromagnetic, antiferromagnetic. So then we say, okay, if we wanted to really predict all of them without this mean field one, we have to include at least one configuration. That'll be antiferromagnetic, because these are also a type of antiferromagnetic. Right? You can see about this way. So we take one more configuration. So now we get the non-magnetic. Now you see it's 1 year later. It's 1 year later. Again, it's Dr. Yuan leading the work. And we get the ferromagnetic is here, and the antiferromagnetic is here. Now it's energy lower. So it's closer now, right? It's closer. Okay, it's closer. So now we have 3 configurations now instead of 2. So now we think we don't need this equation anymore, because we now have the transition between the different spin configurations. Okay, at least we have the major ones. So put them together. Now it looks very nice. So we don't need the magnetic anymore. We predict the transition temperature. So now you may have 2 states. This is the non-magnetic. Okay, this is the combination of the AFM and the FM. Okay, it's automatically separated by system. Okay, so now you see that when you increase temperature, again the entropy term comes to play and make it to be critical point. Now we can even compare more data now. It's actually better comparison with experiment. Talk about the entropy contribution. Previously it was much lower if you study a mean field approach. It's almost a perfect agreement. And this one is also very agreement too. So you have this one is lattice vibrational, semi-electronic, and then with Entropy contribution. It's a beautiful agreement again. So we are very happy. Of course, we know to look at the phase diagram. Okay, now you see that the critical pressure, and the critical temperature, it's very close to the experiment now. Okay, it's very much better than before. Before it's 2.22 gigapascal. Now it's about 2.05. Like much closer to the experiment. And then we can look at the probability of different configurations. At the low temperature is non-magnetic. And then around 300 Kelvin, it starts to decrease. And this is at 2.05, so it's right above here, the single phase above there. And then you can see that around this temperature, and the amount of non-magnetic decreased to 50%. That means 50% of the configuration is non-magnetic. But another 50% is a combination of the AFM and FM. Looks like AFM is the majority. And FM is much less. Of course, we understand because the energy is much higher, right? FM state. Now, if you plot the heat capacity, also look at the reasonable agreement. Of course, it's not very sharp as the experiment. We think it's because we didn't have enough states. We only have 3 states here. You can see it. All right. So again, this was published in 2009 by Dr. Yuan. And then now see we can take the phase diagram from the TP, change the TV. V and P are conjugated variables. So we get a very nice phase diagram. Now the convention based on temperature volume, you get a visibility gap, volume different. Where you, and this is ambient pressure. You got the 2-phase transition here. And this experiment data point. Volume, that's our normalized, okay? And now you see that these are the experiment data points by different experiments at different pressure. And now what you see is that at the critical point, this is ambient pressure, increased pressure to 2.25, 2.5, 3.0, 3.5, and so forth. This isobaric volume, that's some experiment we're talking about. You see, sometimes normal here, normal there, but it starts to change dramatically, and then goes here to infinite. No, that's divergence here. That's a critical point. And then now you see that there's a range here. Okay, and you get an anomaly, or you call it emergent behavior of the system. So some expansion is way larger than anything you have before. All right, so now we want to get a more complex case. Is Einstein pattern. Now one is binary, one component now become binary. But this time we choose a simple case. Again, only one of them is magnetic. If you do ionical, it's more difficult, right? Because you have both of them are magnetic. It's harder. So the Einstein pattern is simple. Now look at some expansion measurements. The symbols are of experiments. You see at 0 Kelvin 0, and when temperature increases, some expansion goes up, and then the system decides, oh, I had enough, so I'm going to decrease, and then become negative, and then goes back again. That's the ambient pressure. So you get a range of anomaly of the some expansion. Actually, all other properties too. Okay. Now this is more complicated because the system needs to be bigger. So the number of configuration 2 to the power of ion atoms. So we took 9 ion atoms, 2 to the 9 power of configurations, at 521, I believe. 512, sorry, 512. And of course, because of the symmetry, so we don't have all of them independent, but you get a multiplicity. So you can count all of them. It's 37 of them. You can see I have 37 of different spin configurations. Spin up and spin down, and we can count all of them. That's a 0 Kelvin EV curve. Now you see a difference, right? In previous case, the metastable one is on the right side, larger volume, but in this case, the metastable ones are the smaller volume. So that's a significance. That's significance. We can see that in a few minutes. So this is for 0 Kelvin. That's good, but we need free energy, so we calculate free energy. That's the free energy. So this free energy is relative to the ferromagnetic. You can see that, right? Based on the free energy itself, the ferromagnetic is always stable. So if you take the energy comparison, there should be no transition. However, you see that the energy difference between the different configurations are decreasing. Then it becomes much smaller at a high temperature. If you look at this range here, around the 200 to 300, that's changed the most, right? Becomes below 10 now, okay? So that means the configuration, statistical probability of the other configuration will increase. So look at these plots here. It shows that at low temperature, 100% of ferromagnetic. When temperature goes around 0.3%, 0.3 of the critical temperature, it starts to decrease. And around the critical temperature, it becomes 50%. So another 50% of all the configurations are not ferromagnetic. And you now can calculate the magnetic magnetization. You can see that there's simple set experiments for neutron and X-ray. And then you can see that our calculations it'll be off, it's not exact. Okay. And we have a little bit higher a temperature for the complete disappearance of the magnetic magnetization. But it's pretty close. Again, you have to remember that we have 512 configurations, and which nature has much more. Now, then we can predict the temperature, phase diagram, temperature and pressure. We get a critical point. So below that critical point, you get a second order, first order, above that, get a first order. Okay. Now, again, remember that TP diagram here, this is negative slope. In the previous case, it's positive slope, right? For cerium, it's a positive slope. So now if we convert this pressure to volume, what do you see? Well, you see the mid-speed gap is the critical point. But this time, the volume, the isobaric volume change is again normal. And it starts to become 0, then become negative, then become negative infinite, then become less negative, and become 0, back to positive. And this is the ambient pressure. These are the experiment data. The lines, the small dots, are from the dot dash line is from calculation. Now you see that in the whole, there's a whole range here. At different temperature and pressure, you get a negative sum expansion. So now the reason is because that metastable configuration have smaller volume. So you have the volume expansion for all configurations, but you have exchange or increase the probability of the smaller volume configurations. So total volume may decrease in some range. Of course, this one is completely predicted from stability, right? But the stability does not predict the sign of it. It will predict it should be good infinite, but then infinite could be positive or negative. All right, so what challenge do we have here? Now we think we have an approach to do that. Challenge is that, well, how do we know we have enough configurations or include the important configurations? Well, we have to compare with experiments. That's what we do now. And it's not about how big the supercell size we should take. Okay, so that becomes very challenging too, because we don't know what the size we should take. And so we have to test it. Okay, so that's the challenge we have, because the importance in that these two combine together, capture the feature of the system, which we do not know at the beginning. Okay? So I hope that down the road from the machine learning side, we can give us an indication, this kind of configuration is important, and this size are sufficient to capture this feature. Again, that will be scale dependent, right? So it's a scale and time resolutions way to dictate which is the size of importance one. So this is our overall entropy approach. But then I thought maybe I should just go broad a little bit about thermodynamics in general. Okay, so I always have this question: is thermodynamics for equilibrium only? And if you ask students, there's a few, maybe half of them say yes, it's equilibrium, and other half say no, it's not, or maybe more they say it's equilibrium. But you look at the first law, it never says it should be equilibrium. It just says how much work, how much heat, how much mass you add. It never says it should be equilibrium. But however, if you look at the Gibbs equation, which he derived in the 1870s, is equilibrium. Because this is, in this equation we learn is for equilibrium system only. So what's different between these two is when we introduce entropy. So entropy is one term was dropped from this equation. It's called entropy production. Because Gibbs was explicitly interested in the equilibrium only. So you drop these terms here, this is zero, this is zero. Okay. So I want you to remember that way I put the y here, y represents all the potentials, temperature minus P and mu I, and the driving force 3, you can see, by the way, separate out. So now if you keep energy now, that means this term, if we only have 3 terms here, it's for equilibrium system only. If we want to talk about non-equilibrium, we have to include this one. So that was the CAFAT does. CAFAT model includes that term in the modeling. Then we talk about all kinds of internal variables. The system doesn't have to be equilibrium. So if that's the case, then we can talk about all kinds of properties. I'm talking about the non-equilibrium system too, okay? That means we can do the derivative between x and y. What's x? X is the model quantity, y are the potentials. So if you talk about the x and y derivative, it's basically a secondary derivative of the internal energy, or the free energy. So the y is here, x is here. So let's give all our properties we're talking about, or most of the physical properties we're talking about. It's important the diagonal terms are always positive for a stable system. That's required by stability. However, all the off-diagonal terms, which are symmetric due to Maxwell relations, there's no laws that say they have to be a sign, a positive or negative, because there's no constraints from the natural laws. So they can be positive, negative, zero, or infinite. That's just I demonstrated for some expansion. Could be zero, negative, positive, or infinite, right? Of course, when they become infinite, all the terms in the middle becomes infinite too. That's what they're common, but they could have different signs. I just showed. So this is one type of derivatives. We'll talk about the physical properties. In the last few years, we found that that kind of derivatives are very useful. It's called, before I do that one, I want to mention about the phase time for the negative properties. Talk about negative sum expansion. It turned out we actually can use phase diagram, potential phase diagram, to determine which phase has negative sum expansion. Remember I mentioned a positive slope, a negative slope. So if it's a positive slope, you have positive sum expansion in the vicinity of the line, phase boundary. That's because entropy, pressure increase, entropy decrease. Okay. And however, for many cases, all the negative phase boundary, you could have negative sum expansion in some range. It's very important, in some range, not everywhere. Okay. So it's because pressure increase, entropy increase. So usually when the temperature increase, right? But the pressure increase, entropy increase too. That's why they do differently. It's because they are not conjugated variables. Okay. So now let's go back. We can actually calculate for example, many cases here, and is that you can do the. I want to emphasize the case we talked about before is for high temperature anomaly. For very low temperature anomaly, you don't need different configurations. You can just do photon calculation. For example, if we calculate the water at low temperature below 50 Kelvin, you can predict the negative sum expansion in ice. Well, not exact ice experiment measure, because we didn't consider the configurations. We only considered the phonon. Same for silicon, only phonon. We forget that the configuration contribution. The reason is because if you think about the harmonic, quasi-harmonic, this is the inverse one, it's called anharmonic. And they can actually think about the combination of this kind of different configurations. Okay. And then if the configuration can be captured by the phonon vibration, that's what the calculation, then you don't need this kind of mixture of configuration. But of course, it will be more accurate, right? Because you have some energy here above the phonon energy we typically do in the calculations. All right, so in the last few years, we found there's another type of derivatives was very useful to us. It's derivative between the potentials. That has been really discussed in the literature. But it turns out it's used broadly in the kinetic transport properties. For example, we put the y here, that's all y. It's all y, that's potentials. Of course, the derivative in the diagonal term is 0, is 1 because to itself. But if you talk about temperature stress to temperature derivative, right? As ferroelectric. the deformation, right? And we worked on one of them, the thermal transport. And Dr. Yuan again. So we had a project in JPL about thermoelectric property. So what is thermoelectric property? It's a temperature change affect the change of electron potential. So electron is going to move because of temperature. So electron moves because the potential is different. So that means this term actually gives us the Seebeck coefficient. So what we believe, the Seebeck coefficient is not a kinetic property, it's complete thermodynamics. Seebeck coefficient contributes to the electron transport by combination of the thermal conductivity times Seebeck coefficient. Turns out that's the equation people use to calculate the current. Okay, so it turned out, I think there's so many properties you can calculate now. Again, this matrix is symmetric based on the Maxwell relation. So it turned out those properties are very easy to measure, and those properties are very easy to measure and to calculate if you know the entropy, right? So again, nice, entropy plays so important role. So any properties related to temperature is related to entropy. So if we can calculate entropy, then we calculate all these properties, and we now save the time to measure. All right, so I put this discussion in my. I do want to mention that it's a paper we just submitted on this one. It's not published yet. Hopefully, it get published very soon. So in this paper, we talk about it, put them together. So we have thermodynamics, conventional thermodynamics about the stability, metastability, instability, but there's a range of new coefficients called cross phenomena, Seebeck coefficient, Sorel coefficient, piezo parallel electric coefficients. They are derivatives of the potentials. And we can even expand further to diffusivity or conductivity, which we did about more than 10 years ago. And many people are working in conductivity now. And I know that Dr. Yuan has a paper on the Lorentz number, which is in the archive. We hope it get published soon. And with the elastic properties and plastic properties, that's a recent work, collaboration with the faculty in our department. So energy together with entropy can do a lot more things than we have started before. With that one, we need tools. I just want to advertise the tools we have. You can go to github.com/research and you can see a lot of tools we have. It's all open source. Again, I want to thank Dr. Yuan, helped me, or actually we wrote together this book. And so Dr. Yuan is really, really instrumental to get us into the quantum mechanics. All right. I want to mention that we have a workshop next week. If you want to join our workshop and talk about the tools we're developing or developing. I give a summary. I hope everybody agrees with me. Entropy is multi-scale and drives all internal processes of a system. And the system can be defined at what you need for your interest of your research. Okay? So it's any kind of scale you want. And the Entropy approach, which we developer can predict anharmonicity, includes its limit at critical points, with inputs exclusively from first principle calculations. And then we have a lot of challenges. Okay, it's going ahead, but that's good. Challenges, opportunities for us to develop better approaches. And then what is the next complexity? We're working on perovskites. Remember, we do pure elements, we do binary, perovskite ternary. And we also work on nicolates. As also ternary system is a type of perovskites with LBO3 structure. We hope we have a paper coming out very soon on these topics. And there are a lot more applications, okay? But derivatives of entropy and properties related to temperature. And collaboration is welcome. If you want to work with us together, we will be more than happy to work with you and develop new theories and new approaches, new tools. With that, I want to thank you for your attention.
So thank you, Zi-Kui, for this beautiful talk. We are open to questions. Directly to the speaker. We don't need to put them on the chat.
We got Corey.
Corey?
Hi, Professor Luth. This was a great talk. Thank you very much for your time. My name is Corey Osis. I'm a postdoc at Duke University, and I had a question regarding slide 18. I'm not sure if it's a trivial question or not, but it seems like you have an interesting insight. I was curious about your discussion about the difference between using energy versus free energy. I mean, I think this is something that I was really just taught and took for granted. But I was wondering if you had a different perspective as to why we use the free energy, maybe from the perspective of entropy from different scales, or from the perspective of the different equations you had of entropy, Gibbs versus the first law, etc. I just wanted to get your perspective on that.
Thank you for your question. That's actually a very critical point, in our opinion, is that, of course, you can do tests, right? Again, you can do tests. You can take the energy only, or you take the free energy. You compare. We did a comparison. We didn't publish that one, but we're going to publish in our next paper to compare the two differences. And I think it's really of course, you know our conclusion is that you need to include it. Otherwise, your prediction will be off by 100 degrees for experiments. Okay. Now, you actually touched that point. The point is that it's a multi-scale entropy. So the entropy of a different state, given the configuration itself, contributes to the total entropy. Okay, so this equation. Okay, and this equation will affect the probability. So because of this contribution, the probability changes dramatically compared to you don't include it. Why is that? Because high temperature phase has high entropy. So it increases the probability dramatically compared to one without it. So this is true. That's why we call it entropy. Oh, we didn't call it before that, but now we call it with the multi-scale entropy. It's really that entropy make the quantitative comparison with experiment possible in our approach.
Okay, I see. Thank you very much. I appreciate it.
Next, we have Simon.
Simon, yep.
Hi, this is Simon Develoff from Duke. So my question is a bit more, I guess, philosophical. So you're talking about this multi-scale approach where you're just subdividing entropy, but you would think, okay, at some point you cannot subdivide entropy because then you would move from the classical regime to the quantum regime, where now you start, rather than, let's say, probabilities, you're dealing with density matrices. So I'm trying to think, there's some maybe intrinsic limit to this approach when, this only works, let's say, if you can represent your system classically or semi-classically. So.
Okay. That's a good question. I tell you, I don't have answer for that. I don't have answer for that. But that's why when I talk with people about quantum materials, right? That's one thing. I say I don't know, So basically that all this one is based on electrons. Okay. So if you go to scale below electrons, I don't know. I don't know what configuration you're going to get. So you can use the quanta as your base component, right? So you see, that's when we move to when we moved from the atoms to electron, we try to predict the Zi-Kui coefficient. Okay, we take electron as one component. So we talk about electron distribution. We talk about the entropy for electrons. So that with some electron becomes very critical. Okay, so that's why when we take that one into account, and then we found that we can do it. So we actually can predict from that equation. Let me see what it is. From that equation, we found that if we take this equation as our base, we found that we can predict electronic properties. So we found that our prediction of the Zi-Kui coefficient is better than the Boltzmann transport theory prediction. Yeah. Because in that prediction, they have a relaxation time. They have a few hidden parameters in that model, which we do not know. So they have to estimate it. But if we predict it from this electronic properties, electrons, then we don't have that approximation. We have two papers that come out. That's much better prediction and more straightforward, and in my opinion, more correct because we don't have that feeding parameters to put in there. Now, if you want to go below electron, I have no idea what it would look like. We have to
Yeah,
change
yeah.
our quantum mechanics.
Yeah, so I mean, at the end of the day, you're dealing with some sort of unit cell, right?
Yeah.
You're dealing with
Exactly.
some sort of unit cell, so some collection of electrons, or
Yeah.
at least one electron.
Exactly. Exactly. So
Okay.
this is complete based on the quantum mechanics theory,
Yeah.
and based on the DIT theory.
Okay, thank you.
All right. That's what we have. Oh, Joshua, raise your hand.
And Josiah.
Hi, I'm Josiah, postdoc at Buffalo, and I noticed on when you introduced the multi-scale approach on 18, you mentioned a lot of things were up for a discussion and evolution, and this has been a really exciting concept and a really exciting talk. But I just among the things you mentioned, you also mentioned that the name was still under some consideration, and if that is the case, I would like to respectfully suggest maybe replacing the M with a S or a Z for like a Zentropy, which might assist in some of the connotations that people get when they see this, and it might help with certain etymologies that nobody gets the wrong idea about what this is. Also, I like the by doing that, you can use the letter Z, which is kind of related to S. And, right. It kind of fits in, I think, really well, and it gives this really nice sense of the sense of a big idea. This multi-scale, it covers small and large things, and it's very calming, and it covers everything really well. It showed up to me toward the end there, and I just thought I might submit that as a consideration for the name.
That looks fantastic idea, because previously called a partition function approach. Then, partition function has so many different meanings, and the Z represents partition function, Zentropy. That sounds fantastic.
Excellent.
Oh, thank you for the suggestion. Because we have not officially published this name yet, except this talk and the talk I had in the morning. Okay, and also in my paper, which is submitted but not published yet. So I'm going to discuss with Dr. Yuan and see if Zentropy sounds perfect. Thank you very much. I like it.
Welcome.
And also, it's a Z here, right? We represent partition function actually goes back to what really this approach about. It's really partition function. Only difference is that takes energies of energy. Thank you very much.
Yeah.
I'll buy you a drink next time we meet.
Looks like we have another question by Andre.
Hi, I am Andris Milaniuk, and I'm postdoc in Stefanos group. Thank you for your good talk. I have a question about your choice of configurations. So I guess you mentioned that you choose important configurations based on experimental data. So I have two questions. One is, what would you do if you don't have experimental data? And second, how would you actually not quantify, but do you have any means of saying that, okay, if I can have one set of configuration or another set of configurations, how can I say which one would be the best?
That's an excellent question. That's what we're working on now. Okay. So to answer your first question, we do not know. So you have to do iteration. You have to predict it and experiment and predict the experiment. This iteration is important. Okay. Or hopefully we can build up a big database, which will be billion configurations instead of a million we have now. Okay. So that means if we have that big configuration database, then we suppose we can predict everything, just like a human genome, right? You have hundred thousands of genes, but you have billions of pairs, chemical pairs, right? So that order of magnitude has to be changed. That answers that question. So, but hopefully our physical physical intuition will help us to provide some good ones. Okay, so I think it's really not completely computational, but it's the machine learning combined with the physical intuition. Okay, so we take the important ones first. And at the end of the day, maybe after another 50 years, we get all the configurations we could imagine, and then we don't need the intuition anymore. Okay, that's the first one. The second one actually even more important. So you have to be able to quantify the uncertainty, basically. Okay, that's all we can do. So that way it's precision, right? The precision point. So you can add more configurations and then see how you converge your prediction. Okay, that way you actually can do today already. You can just add more configurations and see how the results change. Okay, you can change your size and see how your prediction changes. If your prediction becomes stable, then you say under that framework of definition, you get the best results you have.
I see. Yeah, thank you.
ZK, I have a question. I tried to ask a question before, but the computer bombed, so maybe it does not want like these questions. So you have a gamma cerium and alpha cerium, right? Page 23. And thank you very much for putting page numbers. Right, it makes our life. I think I think next one, 22, right? Okay. So listen, what happens? Previous one. Yeah, that's it. Okay. So what happens in the middle of miscibility gap, right? So do we have some sort of bimodal decompositions near the solvus, and some sort of coherent spinodal decompositions, or even incoherent between grains or organizations of gamma cerium ferromagnetic and alpha cerium non-ferromagnetic different volumes?
That's right, you have it. Exactly. You can spinodal.
You have spinodal. So, but is this spinodal, the configuration of this spinodal is going to be the one that maximize the multi-scale entropy? Because there are a lot of different ways you can entangle these spaghettis, right?
Yeah.
These noodles,
exactly.
right?
Yeah, exactly. So the idea is here is that you can have different configurations that can arrange in space.
Okay, that's very interesting. Yes.
But the important thing is that the arranged space is not static; it's dynamic arrangement. They change all the time. They could.
It changes all the time. Yes, but it has an activation energy to change, right?
That's
if you are a low temperature, it's going to get stuck. If you are near TC, these spaghettis are constantly rearranging in the space of max S, right?
Yeah, yeah.
Okay.
Absolutely true. Absolutely true. And of course, now you can take the phase field to simulate morphology. That's in a condition, right? As phase field give you morphology for that. Yeah.
Yeah. Okay. Yeah, because this because your thermodynamics is not thermostatic, so even your multi-scale entropy needs to give a dynamic equilibrium, not a static one. Yeah, that's correct. Yes.
Exactly.
So do we have other questions? And Marco, thank you
very much. Yang has a question there.
We have one more question.
Hello, I'm Shuhao Yang, a PhD student at UC Davis. I'm now in the Professor Alexandra Nivlaski group at ASU. I'm an experimental thermodynamic people. Our experimental thermodynamic people, when we want to measure the entropy, we always measure the heat capacities and then calculate the configuration entropy based on the crystallography structures. But my question is, if we also want to use the term of the entropy, does it mean that we also, besides the heat capacity measurements, we also need to measure the thermoelectric or the thermomagnetic, all these properties, and then combine them together to get the entropy? So from the experimental measurements, how to get to the entropy?
I think it'd be very hard, in my opinion. Okay. In my opinion, the best way is combine computation experiments together. So you take the advantage of the computational approach and take the experiment approach. So experiment measures overall behavior, right? All combined together, okay? And it's very difficult to decouple it in the different contributions. But then it takes computational to do different contributions. Now, if you want to separate them, then you have to do the spatial resolution. You have to do the higher spatial resolution to get the different configurations. So that's what it shows is for the latitudinate, right? The idea is really that, for example, in this case, basically, you really need to measure all kinds of these different configurations. And then you need high resolution. Okay. So experimentally, you basically do different scale measurements. You do a high scale measurement, a low scale measurement. Okay, low scale measurements give you different configurations, then put it back together. So actually, low scale measurements is also a way to confirm the configuration used by computational work.
Especially like the lower temperature heat capacity measurements, when we do the fitting of it, we use the different functions to fit it, and in that we consider, or we already consider the like the electric or magnetic factors, the contributions. So my question is that the heat capacity measurements is still good enough to get the entropy terms, or we need to still, from the experimental ways, we still need to consider more things rather than not only the heat capacity measurements.
I think so that depends on what entropy you're talking about, right? If you talk about the total entropy, that's enough. Because you're measuring heat capacity, you measure this one. But if you understand the individual ones, then not enough. So the scale issue, the scale, right? If your scale is, if you stay in the scale you have, this diagram, if you stay on this scale you have, that's perfectly okay. But if you want to understand the scale beneath it, you want to understand why it happens here. And then you will need a smaller scale. And then that's not enough.
But you know, in thermodynamics, there are not only the entropy, there are also entropies. In most cases, the entropy is the dominant rather than compared to the entropy.
Well, I disagree on that one, because it's the second law, that's entropy drives the change. Okay, that's second law. Right? It's not entropy drives the change. We don't say that. We say entropy drives the world. Entropy, right? We didn't say entropy drives it. Because second law says entropy production. So it's not an entropy production. Okay. Any change is driven by entropy in principle. Entropy drives the change.
Yeah, thank you for your answer. Very good, very great talk.
Thank you.
Well, it is nice to have questions that are from all over the place because scientific argument is welcome, right? So it's nice to. It's always nice to think in a variety of different ways. Yes. So, do we have any other questions from the audience? Okay, so it looks like we don't. So I want to thank again the speakers, and let me before we leave the day, let me remind again all the audience. Some came late, so please subscribe. Go to aflow.org/seminar. Please subscribe to all our future seminars, so I do not need to keep sending emails reminding. So we saw this beautiful talk by Entropy. In a couple of weeks, we're going to have Asta, then Dabo, then Mazin, then Carbonio, Boeri, Gao, etc. You see all we are kind of booked until January and February. Please subscribe, keep an eye on our page, and very soon there will also be a link here. There will be a link under Zi-Kui with this talk that we have recorded and is going to go on YouTube. And I want to thank you very much for coming to the talk, to the audience. Thank again to the speaker for his wonderful talk. I hope that I will be able to visit Penn State after all this COVID mess. And thank to everybody. And let's reconvene in 2 weeks.
Thank you. Thank you for having me here. Thank you a lot, everybody. Please be in touch so we can work together.
Exactly. We are looking for a macroscopic, not multi-scale, macroscopic entropy, right? Thank you. Exactly.
Thank
That's the
you.
one. Good. Thank you.